Hi, so today we're doing something different. The other more video essay-like format is still going to continue coming, don't worry, but this week I wanted to solve a physics problem with you, the problem of the elastic pendulum or the spring pendulum, which is basically to figure out what happens when we have a spring that is connected to a fixed point on one side, and on the other side we have like a weight, like a ball, for example, and we let it freely swing. And of course, it's going to bounce up and down and move to the sides. And here we have only 2 dimensions. So we could theoretically do it with 3 dimensions, like let it swing forwards, backwards, side to side, and so on. But here, let's solve a more simplified version. So Lagrangian mechanics are a way to figure out the equations of motion, to reach the equations of motion of a system based only off of the energies involved in that system. So we're going to see that we only need the kinetic energies and the potential energies, and we're going to put that into a big function called a Lagrangian, and then we're going to use the Euler-Lagrange equations, which are just derivatives of that big Lagrangian function, and they will give us the equations of motion. So let's start. I've drawn here a little diagram of our situation, of our system. I put the origin of the coordinates at the point where the spring is connected. So that's not moving, that's not going anywhere. And that's our origin. So we have the x-axis going horizontally and the z-axis not going up, but going downwards. And I mean, you can choose both ways. You're just going to get a minus sign at the end. But I like to choose in this situation, or in situations like this, the z-axis is pointing downward, because the ball is never going to go up anyway, unless we start it there and let it fall. So I'm just putting this here so that we get only positive values of z. And the first thing I'm going to do is already here on the screen, which is define polar coordinates, right? So even though I am defining this Cartesian coordinate system, I am going to be using polar coordinates, meaning we're going to use the angle, and we're also going to use the size of the spring. So we're going to use rho as the size of the spring, meaning how far away our ball is from the origin, and also theta, the angle that this spring is making with the z-axis. And so we write the relationship between our Cartesian and polar coordinates like this. So z is going to be rho times cosine of theta, and x is going to be rho times sine of theta. These relations can be derived by just drawing triangles here in the diagram. But if you don't understand them and you want to see how to do them explicitly, just leave a comment. I might do a video about that at some point. But yeah, now that we have those relationships, let's figure out what are the energies that are involved in this system. So first of all, we have the kinetic energy of our ball, of our weight. So let's go ahead and write out the expression for the kinetic energy. The kinetic energy term here is just going to be the usual mv squared over 2, where m is the mass of our particle, of our weight, and v squared is just going to be the square of the velocity. And in here, we have that the velocity can be decomposed into the velocity in the x-axis and the velocity in the z-axis. And then I just wrote that out here, x dot squared plus z dot squared, where the little dots just mean a derivative with respect to time. And because it's going to be easier to work in polar coordinates, I wrote explicitly the expressions for x dot and z dot with respect to our polar coordinates, right? Which just means I took this definition here and I derived with respect to time. You get a product rule, right? So you have rho dot sine theta plus rho cosine theta theta dot. Again, if I'm skipping too many steps, or if I'm going too fast, just let me know. I can also do some videos on calculus maybe. Okay, now inserting these explicit expressions into our kinetic energy term gives us the kinetic energy in terms of the polar coordinates. And what we get at first looks very scary. When we expand the squares here, we get this giant term. But actually, it's going to simplify a lot, because if you notice here, this cross term is exactly the same as this cross term, and you have a plus and a minus, so they're just going to cancel each other out. And in here, these other terms are also very similar. Take a look at these two here. They're the same thing, but one has a sine squared, the other one has a cosine squared. And as we know, sine squared plus cosine squared is just going to be equal to 1. So if you take this factor of rho dot squared out of these two, you're just going to be left with rho dot squared. And the same thing can be said for this pair of terms here. And at the end, we're left with something that's actually pretty friendly for our kinetic term. It's just our m/2, which was already there, and this sum of velocities. And a sanity check that you can make is whether the units still match out, and they do, because here you have velocity squared, and here you also have velocity squared. This might not be obvious at first because you have here distance squared, and this is something that looks like velocity, but actually this is angular velocity, which is not meters per second, it's just 1/second or radians over second, but radian's not actually a unit. So at the end, you just have velocity squared, and that actually makes sense. So we've got our kinetic energy. Let's see how potential energy behaves in this case. And we're actually going to have two potential energy terms here. One of them is going to be gravity, and the other one is going to be from the spring. So the further away you are from the origin of the spring, the more force it's going to try to push you back with. The gravitational term is just going to look like mgz, the usual thing, mass, acceleration, and your height. But in this case, you get a negative sign because our z-axis is pointing downwards. So as z grows, our energy decreases, right? Because we're going down. And here we can choose the height for 0 potential energy. And I just chose the height z equals 0 because it makes everything easier. So when z is equal to 0, the whole gravitational potential term is also going to be 0. And now for our elastic potential energy term, we're just going to have k, which is the spring constant, meaning how difficult it is to stretch that spring, how stiff that spring is, also then divided by 2, and rho squared, which is the distance from our spring, meaning the further away you get from the origin, the more you stretch the spring, the more it's going to try to bring it back to equilibrium state. Something that's always nice to notice is how close this term is to our kinetic term. So it's mass, meaning how difficult it is to move something, times velocity, meaning how much it's moving. And here, we also have how difficult it is to move the spring versus how much it is moving. And so we have all the terms we need. Just one detail, the gravitational term here is still written in terms of our height. We need to make that substitution here, z equals rho cosine theta, and then we already have all our terms written in polar coordinates. And now that we have all the energy terms that are going to be involved in this system, we can sum everything, but not exactly sum everything, but we can write everything together into something we call a Lagrangian function, or just a Lagrangian, which is represented by this L here. And what it is just the kinetic energy minus all the potential energies. Now, I'm not going to go into how we derive the Lagrangian and what it is exactly. It's just a measure of the energy of the system. It's not the total energy of the system, because of course there's the minus sign there. What's important now is that it's a term that's going to give us the equations of motion. And again, if you want me to go deeper into what a Lagrangian is, maybe explain Lagrangian, Hamiltonian mechanics in more detail, let me know. That would probably be something I'd be interested in doing. But what is important right now is that we have the three terms that we've derived, our kinetic energy term, and then minus our gravitational potential, minus our elastic potential. And here I just wrote everything explicitly. Remember, this was minus mgz, and then I just substituted z for rho cosine theta. And now that's why it's positive here. And then minus our elastic energy term. So how do we get from this Lagrangian function to our equations of motion? Meaning, how does theta and rho change with time? Because if we have an initial state, let's say it starts at an angle and with a specific distance, how does the system evolve in time? Those are the equations we want. So what we're going to do to find the equations of motion is input this Lagrangian term that we just calculated into what are called the Euler-Lagrange equations. These are derived from first principles, specifically from the principle of stationary action. And these equations give you the trajectory of a particle, the trajectory of a system from one state to another. But note that we are deriving here, right? We're differentiating with respect to Q. Q is just a name for one of the variables, one of the degrees of freedom of your system. And here we have 2 degrees of freedom, right? We're in 2 dimensions. And more specifically, our degrees of freedom are rho, our distance from the origin, and theta, our angle, right? As defined here. And just a detail here, I defined the equilibrium position of the spring as being the origin. So that's why I just wrote k over 2 times rho squared. If you want to solve this problem in a very, very general way, you actually need to do like rho minus rho 0. This rho 0 would be the equilibrium position. So for example, this spring might not be wobbling about the origin. It could have a different point that it could be wobbling about. Here I'm just assuming that rho 0 is equal to 0, but just to let you know, you don't need to do that. Anyway, Q here is each of our degrees of freedom, meaning that we're going to have one equation for rho specifically and another equation for theta. So let me show you how that looks. So now we have substituted Q in here for each of our degrees of freedom, rho and theta, and now we have these 2 equations. The only thing we need to do now is basically maths. So we just take this big equation here, our big term for the Lagrangian, and then we differentiate with respect to each of those variables. So after calculating the necessary derivatives and writing them down here under their respective equations that we're going to use them in later, there's some things that are interesting to note. For example, this derivative here looks a lot like momentum, mass times a velocity, and that is no coincidence. Again, there's a lot of things in classical mechanics that turn out to be the things we expect them to be in some cases. The equations of classical mechanics, or the whole logic of classical mechanics, of course, has to reduce to Newtonian mechanics, right? Which is what we usually know. So for example, other thing is this thing, which is m times a, essentially, right? Mass times acceleration. So our equation of motion is going to look something like mass times acceleration equals something, right? And this something in most cases is going to be some sort of thing that we can describe as being like a force. Okay, so now let's substitute in all these terms, specifically this one and the third one in the first equation, because this one is just like intermediate, right? I calculated this derivative, but then I also got the time derivative out of it. And well, we don't need this term in the final equation for anything. And on the second one, we're going to use this one and this one. Same thing. Detail here is take care when you're taking those derivatives, because not all of the derivatives are partial. So for example, this and this, you are considering everything else to be a constant if it's not the variable that you're interested in. So for example, if you're differentiating with respect to rho, everything that's not rho is a constant. So theta, even rho dot, that's also constant. But in some cases, for example, you have this derivative here, take care, because you don't explicitly have time in the equation, right? You don't explicitly have a t here, but every one of these functions are all dependent on time. So remember, chain rule, product rule, whole thing. That's why you end up with a big term like this one, for example, because the term that we were differentiating depends on both rho and theta dot. So you get both a chain rule and a product rule here that we have to deal with. Anyway, let's substitute them in and I'll show you the final equations. So these are our final equations of motion of the system, meaning that for every initial state, this is how the system is going to evolve. So according to this thing and this thing. The first lines in each case, like here and here, are just the raw substitution, right? I substituted this term and then this term and then this term and this term and so on, equals to 0. But this second part, this circled part here, is a little bit of a rewrite of each equation. In the left case here, the equation for rho, I just wrote m rho double dot alone on one side and then everything else on the other side to leave it in that format, right? In that shape that we know from Newtonian mechanics, right? So m rho double dot, which is essentially mass times acceleration, is equal to something that has the units of force That's very cool. You can check it for yourself. These have units of force. And specifically, this is the spring force, right? K times the distance. And this is the gravitational force. Cool, right? And then the other side, same thing. Of course, this is not exactly mass times acceleration because of the units of theta. Theta is an angle, so it doesn't have the units of length that you need. But then that's why I left one row here. Before I rewrote everything, we had a rho squared. But then again, we also have rho here and rho here. So we can divide everything by rho. And the terms that are left are also forces. For example, this one is the other component of the gravitational force. Isn't that cool? Yes, right. So this is the problem. We solved it. Of course, it depends on your initial conditions. Maybe if you're solving an actual like problem for university or for a course or something. Anyway, that was it. If you have any questions, just let me know. If I made any mistakes, just let me know, because of course this is something that I've done a few times, not only in this problem, but many different kinds of problems. But that doesn't mean I'm not going to make a mistake. I probably have, but this is always so much fun. And as I said, I got the idea to do that because somebody asked me a question and I answered and I like replied to them, but not with much detail. And I like explaining these kinds of things. And I think this is a good example of why Lagrangian mechanics is so powerful, right? You only need the energies. Like, of course, this takes a while, but you only need the energies. And that's the difference between this and pure Newtonian mechanics, while you usually work with the forces. In this case here, the forces are difficult and there's a lot of them, and then they depend on each other, they're coupled. So it's a difficult problem to solve with Newtonian mechanics alone. So working with the energies, which are scalars, meaning they're not vectors, you don't need to deal with vectors at any point, this can be easier. And especially when you have more difficult problems, because you can have like double pendulums, triple pendulums. Maybe they're swinging around on a point that's not fixed. Maybe the point's fixed, is moving around. Anyway, there's like thousands, millions, infinite amounts of different problems that are easier to solve with Lagrangian and or Hamiltonian mechanics, which is kind of similar. And yeah, this has been a blast. This has been great. Let me know if you like this kind of stuff or if you like the other video essay type video more, or if you want to see both, or I don't know. Just write in the comments and I'll see you in the next one.